28,000 divided by x squared. Is this okay? We have to find the least common denominator. Who would like to tell us the least common denominator? Anyone who hasn't said anything yet, please.
X squared.
Very good. So then we need an x squared here. And then what do I write at the top? 2 x to the good minus 128,000. Good. So we want a prime of x to be 0. What do I have to write next? Anyone, please. Anyone?
We write the what we just got, the 2x to the third minus 128,000 over x squared equals 0.
Yes, but when a fraction is 0, only the numerator can be 0. But yes, you're right, I'm lazy, I didn't write the intermediate step, but I wrote this. Okay, you're right. So now we divide by 2 and move this to the other side and we get 64,000. What now? Any suggestions? Anyone, please? Anyone?
Hebrew.
Thank you. Thank you very much. So then we have x equals, is it 40? And the measurement unit?
Centimeters cubed.
Careful.
Squared.
Careful. X is just a length. Right? X is the base, this measure of the side. So I claim that x equals 40 will result in a minimum, the area minimum. I must show why. This is not good enough. So here's how I show why. Of course, this is not possible. Infinity is not possible here. Anyway, good. So here's my derivative. I will not study the sign of the denominator because it's a waste of time. But when I plug in 0 in the numerator, what will be the sign of the derivative here before 40?
Negative 120,000.
Of course, negative. We only need the sign. And on the other side, if I put 100 here or anything, it will be positive. So now I know that this is typical for a minimum. So it's guaranteed that whatever number I'm going to write here, so I'm going to determine a of 40, that will be guaranteed to be the minimum. So if the box has 40 by 40, and the height will be determined in a moment. So 3,200, so the height, not 3,200, it's 32,000 divided by 1,600. That will be the height. And I get 20. This is guaranteed to be a minimum surface area. What is the minimum surface area? The surface area is x squared plus 4x plus h. It's easier for me to put it here, or we can plug it in here. So 40 squared plus 128,000 divided by 40, and that's the minimum area. It doesn't matter which formula we use. So let's determine that. So the minimum area will be 40 squared 1,600 plus 128,000 divided by 40. So that's what it is. So what do I get here? 32,3200 plus 1,600. I got 48. 4,800 squared centimeters indeed, because it's the area. and it's guaranteed to be the minimum. So if we are the production manager for this factory, for whatever reason, they are making this box, you will tell the manager, sir, if you want to use the minimum possible surface area or material for these boxes, knowing this constraint, this is a constraint. Each box has to hold 32,000 cubic centimeters. This is very important. If you want that to happen and you want to use the least amount of material, make sure that the base has a side of 40 centimeters and the height has the height is 20 centimeters, and you will get, I guarantee you that the minimum surface area will be used for 4,800 of squared centimeters. Any questions on this problem? Is there anything that you have doubts about? It is not sufficient to say, I got X, it's 40 centimeters, move on. No, I must show Y. And we know why. If the derivative changes sign, is 0 or undefined, and it changes sign at a particular X value, and it changes sign from negative to positive, this must be guaranteed to be minimum, and no other. So this is mandatory.
Professor, would we ever have to graph this?
No. No, in optimization, rarely. Who knows what kind of problem, but you may come across, but I will not ask you to graph something like this. No, no, no.
Okay, thank you.
No, thank you. In this situation, we're only interested in finding the max min. Back to the book. Any questions on this? Do you feel a little bit better about it?
So this is like technically, the 4,800 is technically the like absolute minimum, right?
Absolute minimum.
Okay.
If you tell the production, you tell the manager of the factory, sir, ma'am, if you change this from 40 to 39 or 41, or change this into 19 or whatever else you want, you're not going to get the minimum. If you want to use the minimum amount of material, listen to me. This is what has to happen. The base has to have a length of 40 and the height of 20. To meet your requirements of a volume of 32,000 cubic centimeters and have the minimum possible surface area.
So remember, like earlier in the chapter when we're doing the absolute minimum and absolute maximum, we also had locals, and we also had cases where sometimes there's 2 points that share the same minimum. Is there ever a case during optimization where that might happen?
It could be. Excellent question. You could find for the same function, you may be even asked to find a minimum and a maximum. You may find that 2 are possible algebraically, but one could be, for example, 0. You can consider the base of the box as 0 centimeters, right? So you may get algebraically 2 solutions. You may get, for example, 5 and 100, but 100 will not work because the volume will not stay at 32,000 cubic centimeters. So, but it is possible that more than one answer is correct. It's a very good question, Mark, and also you have to go back and check and see what's happening with those solutions, if they are even possible. Algebraically, you can find two solutions, but sometimes both work, sometimes none, sometimes one. Very good question. Thank you. Okay, I'm sharing the screen again. So that was the box situation. I would like to look at something like
What was the number of the problem that we just did?
This was problem 18. A box with a square base and open top must have a volume such and such. 18. Thank you. Okay. So here's another situation. I'm reading several of those and see which one you will be interested in. Find a point on the curve that is closest to the point 3, 0. That's another interesting situation. Find the area of the largest rectangle that can be inscribed. So now we are getting sophisticated. Inscribed in an ellipse, such and such. Again, this is another sophisticated situation. A right circular cylinder is inscribed in a cone. Find such and such. This is a situation in which is a window and the top of it has a half a circle. It's called a Norman window. That's another situation. This is something that basically is exactly what Mark was just asking a minute ago. Problem 43. That's exactly what he's asking. This is another type of interesting situation with a poster. Margins are such and such, and the top, and we want to determine the largest printed area. That's one other. And this is exactly what he asked. And as you see, this problem has basically a maximum and a minimum. So a piece of wire 10 meters long is cut into two pieces. One piece is bent into a square and the other one into an equilateral triangle. How should the wire be cut so that the total area enclosed is a maximum and a minimum? Okay, another situation is with a fence. We can look at that too. Cone-shaped drink. Okay, this is also another interesting situation in which we have, but we can do 50 as well. So anything interests you from what I just pointed out that you would like to continue with?
That one with the poster frame sounds kind of interesting.
Okay, so let's look at the poster frame. Where is it?
It's like 41 or something. Or no, 42.
42. Okay, very good. Here it is. So 42. Poster is to have an area of 180 squared inches with 1 inch margin. So I'm going to copy and I'm going to stop sharing in a moment. It says 1 inch margins at the bottom and sides. Okay, fine. 1 inch, 1 inch, 1 inch. Okay. And 2 inch margin at the top. Okay. What dimensions will give the largest printed area? Okay. So this is the printed area. So again, let me just go back for a second. It said a poster is to have an area of 180 squared inches. So the whole thing is 180. And it has margins. And then it has the printed area. Okay. So this whole thing, I'm going to call this X. I'm going to call this Y. This is X. This is Y. So that's one option. Another option is to call this X and call this Y. It doesn't really matter. It's up to you. We can call this X and then this Y, and then I will change this dimension into something else, and you'll see in a moment what it is. Let's go with the second option. Okay. So if we denote X and Y as the longest side width and length. So then I know that here I have X comma Y equals 180. But I'm interested in discussing this area. I'm going to call it A1, not to be confused with that. So we want to maximize A1. This is our target. So it says, find x and y, having the following constraints, so that A1 is maximum. Okay, fine. I have to find a function that represents A1. Can anyone tell us how to start writing A1? Anyone who hasn't said anything? Josh, Sarah, Isaac, anyone?